More than 2 billion people across the world lack access to essential medical products due to poor quality or even non-existent infrastructure.
Airplanes are amazing because of how they can fly direct A to B, but they're limited by the fact that they're expensive.
Amazon Prime Air could save the company $47 billion per year in shipping costs, and drones could permanently replace $127 billion worth of human effort.
A climbing team could spend days looking at
sometimes dangerous place to be. It's a very hostile environment.
Our team includes Ali Rizvi, Khwaja, Ramin and Mehdi. The problem statement: building a drone capable of autonomously navigating by constructing a 3D map of its environment with AI-based landing.
So let us now briefly discuss about the significance and impact of this project. Machines are known to be efficient. By an efficient drone, we mean a drone that is able to perform tasks at much higher speeds as compared to a human labor. Similarly, a drone that is able to accurately predict its location and its environment and is able to execute tasks with high precision comes under the category of accuracy. The third and most significant impact of this project would be its autonomy, which just means that it is able to perform its tasks so well and so intelligently that it can completely replace a human labor. So one of the best things about drones is that although they can be damaged, but unlike humans they cannot be injured, which makes them perfect for applications which have safety concerns such as inspection of tall infrastructures or disaster management. Last but not the least, drones are known to have a significantly reduced environmental footprint when it comes to other ways of doing tasks in industry, in surveillance as well as in delivery services.
Okay, so now we will discuss some of the existing solutions. The first existing solution is a Sparrow autonomous drone by Percepto. It has three key main features. First, it is fully autonomous. Secondly, it has in-sight automation. And lastly, it has advanced safety features which allows it to navigate through its environment with safety precautions. The second existing solution is by Skydio X2. It has 5 main features: GPS night flight, obstacle avoidance, advanced AI pilot assist, autonomous data capture, and lastly connected flight operations. All these features allow the drone to better understand the environment. The last existing solution is by Azure Drones. It has the following main features: 100% autonomous, GPS night flight, scheduled missions, and easy to use video management system.
So the basic problem that we are trying to address in any autonomous robot is to understand its environment, that so it can map its environment and what it's like, and it can localize itself within that environment. So it knows where it is, and it knows what exactly is its position in that environment. If it knows these two things, then it can easily path plan to go from one point to another while avoiding obstacles. So there are multiple SLAM algorithms available, and most of them have ROS packages available. So these are some of the algorithms that we found in review papers, and they use two main perceptors, either a LiDAR or a camera, and we have shortlisted 3 of them that we will be studying further and using them in our project. First is the Orb SLAM, RTAB map, and the last one. All 3 are visual SLAM methods. They all have their advantages and disadvantages. Some are good at map density, some have better pose estimation, some have loop closure, or some don't have loop closure. So regarding perception, as we mentioned that different SLAM algorithms require different perceptors. So there are 2 main categories. We can either use a LiDAR for perception, or a camera. Now within LiDAR there are 2 types of LiDAR: a 3D LiDAR or a single ray 2D LiDAR. So a 3D LiDAR is a good choice because it does map the environment pretty well and it gives a good depth information. but however it is very costly, so costly that even Tesla doesn't use it in its products. A 2D LiDAR is somehow useless for us because our drone operates in a 3D environment. Now the second option we have is to use a camera. Now again, there are three types of cameras usually available for such applications. The first is a mono camera, which is simply a single camera. The problem is that it doesn't have a depth information, so it generates sparse maps and relies on a lot of features. Stereo camera is similar to mono camera, but with two cameras. It gives some information about the depth, but again, both mono and stereo cameras suffer when the environment is does not have a lot of features. So for example, if a drone is over in a warehouse, in an empty warehouse, where it does not have many features to detect or many corners, to put it more in layman terms, then it suffers very badly. So the best option that we have right now is to use an RGBD camera. So an RGBD camera is a camera with two sensors. One is a normal camera, and the second sensor is an infrared camera. So using the RGBD camera, we can not only measure the intensity of a pixel, but we also know how far the pixel is from our camera frame. So this is the option that we are considering for now. So moving on, this is a general UML diagram of the project as well as the deliverables. So the main component, of course, also this diagram also translates to a ROS node diagram. We will get to ROS in a minute. So the main object over here is the drone, which has all the sensors and control algorithms and all the sensors such as IMU, inertial measurement units, cameras, and so on. Data from the drone, such as video as well as inertial data, is sent to the SLAM algorithm, which runs the SLAM algorithm and computes the map as well as the pose or the localization information of the drone. This is sent for post-processing, where the 3D point cloud is processed to make it more to remove any noise and so on. And the processed map as well as the pose is sent to the path planner. Now the path planner works in conjunction with obstacle avoidance as well as smart landing nodes to make sure that the object follows the desired trajectory, while also making sure that it avoids any obstacles that may come in the way at runtime, which are not present in the original map. Now smart landing will only ensure that it does not land. So for example, if we have specified a spot to land and that spot has some obstacles, then it should compute itself to land at a nearby spot. Now the path planner with the corresponding nodes sends the command velocities to the drone. Now the command velocities tell the drone that where it should move given its current location. So the command velocities will include the linear as well as angular velocities of the drone. All these data and everything will be sent to a visualization tool which is called RViz in ROS nomenclature, and there we can see the map being built in real time and the localization of the drone and all the drone feed of data or video feed from the drone and so on. Now an important question over here is that why are we thinking of using ROS? So ROS is the main benefit of ROS is that we do not have to start from scratch. So we do not have to write the ORB-SLAM algorithm, for example, from scratch. We can already get a open source package and we can integrate it in our application, and we can make the changes because it's open source. Now there are multiple packages of many different SLAM algorithms. For example, in the previous slide we showed different SLAM algorithms. All of them are available as ROS packages. Moreover, ROS is multi-platform and language agnostic, which means that it can be operated on different computers. So for example, I have a main node which is my laptop, and it's communicating with a say Jetson Nano, which is communicating with a Raspberry Pi and so on. It's language agnostic, so the nodes can be written in different languages, mainly Python and C++, but there are all other languages such as Java are also supported. And it is widely used in industry and research. So for example, the Spot robot you see over here by Boston Dynamics comes with a ROS interface. So the novelty that we plan to achieve over here is to improve the end-to-end pipeline of the algorithm. The improvement may be in the application domain or in the or in some subcomponent, such as the post-processing of the map and of the 3D map, or so on. So that is it from us. If you have any questions, please feel free to reach us out over email. Thank you for watching.